All right, so this is the atomic history notes. It should be straightforward, but these are a lot of names and people you need to know. It's not so much important to know the date as it is that you're clear on kind of who discovered what and kind of how they did it. So what is an atom? We talk a lot about an atom because it's such a fundamental concept and fundamental particle in nature. So remember that an atom is the smallest unique particle of matter. The first concept of atoms actually came from the Greek philosopher whose name I can never pronounce correctly, Democritus. However, his was just he theorized that you should be able to get to a point where you can no longer get to anything smaller. His actual thoughts were actually kind of counteracted by Socrates and Aristotle, who were the dominant philosophers of their time. So his ideas weren't really looked on well for a very long period of science. But eventually, we actually realized that Aristotle didn't really know what he was talking about. However, it wasn't until science got involved that we really got clear terms. So the first scientist to really do much, or the first scientist to really investigate an atom was an English chemist. He was actually a teacher. Yay, teachers! Called Charles Dalton. And he performed some of the first experiments that still actually influence and guide our modern thinking on what an atom is. And while some of his stuff was shown later to be incorrect, the key concepts that he worked with were there. So Dalton's theory had 5 key parts. He believed that all elements are composed of atoms. Atoms are indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different. I know this sounds silly, but at the time it was pretty revolutionary. And compounds are formed of joining 2 or more atoms together of different elements. So Dalton's model, we have this cool little picture here. Dalton's model, this really was his kind of model. He saw it as a sphere. Because they are indestructible, he thought there was nothing smaller. So Dalton's model basically is kind of like a marble. He saw atoms as the smallest particle of matter, period, and it was indivisible beyond that. So the next one we talk about is J.J. Thomson. J.J. Thomson, the plum pudding model. He was the first one to actually show or find any evidence that actually atoms were smaller. And the way he did it was kind of interesting. So the Thomson model, he called his model the plum pudding model. This is a very British thing to do. Plum pudding is a type of English dessert. It's basically like a baked cake with raisins in it. So think of it almost more like a chocolate chip cookie, except instead of being a cookie, it's a sphere. So a completely round ball made up of delicious cookie material with chocolate chips studded all throughout. So what his model was this idea of the atoms were made of a positively charged substance. And he didn't know what it was. It was just some substance. In this picture is all this yellow stuff here. Positively charged substance. And then there were these negatively charged particles, these electrons, all scattered throughout, like chocolate chips in a cookie. But it is he was British, so they called it a plum pudding, which is, like I said, like a cake with raisins. It's British puddings or cakes, and crisps or chips, and biscuits or cookies. So gotta love English. So the way he discovered this was interesting. This thing right here is called a cathode ray tube. If you remember the old TVs, or the big ones that we used to have before we went to flat screens, those were used a similar technology, just a little bit more advanced than what he had. Basically, he was passing an electrical current through a gas. So inside this chamber is a gas, and then he attached a positive and negative charge to either end and ran the current through the gas. As the current was going through the gas, it gave off rays of negatively charged particles. And you could see this in part because there was a positive-negative sensor there and actually moved things around. So this surprised Thomson because the amount of the atoms of the gas were uncharged. So he knew the gas that he put in there was neutral. There was no charge. Yet somehow, when he put a current through it, there was this movement of these negative particles. And so he had to figure out where exactly they came from. The only conclusion he could make was that they came from within the atom, which was pretty crazy, because at this point they were still going off of Dalton's model, which is the idea that atoms was solid, like a marble. So something smaller than an atom had to exist, which meant that atoms were divisible. This was crazy revolutionary. Okay, this was Dalton. Dalton was the first. Remember, Dalton was the first one to do any real science on any of this kind of stuff. And the fact that everyone was like, "All right, cool. He did this. He did a lot of research actually." And like, makes sense. We're good. Oh wait, no, look, there's something smaller. So today we know those as electrons. So he knew they were electrons. He knew there was something smaller, but he also still knew that the atoms were neutral, or the gas was neutral. So these electrons were coming from inside the atom, and they were negative, so they had to be coming somewhere. But if the gas was neutral, that meant there had to be something positive in the atom to counteract it. But he couldn't figure out what, and he could never find it. So that set the stage for one of the most famous experiments in chemistry, and one that science teachers like to talk about a lot. And that was Rutherford's gold foil experiment. So Rutherford this is 1908, so we've only known about this stuff for like 110 years. He was a physicist. He was working on an experiment that didn't actually have much to do with atoms necessarily. His experiment involved firing these small positively charged particles at a thin sheet of gold foil, which is only like 2,000 atoms, I think. Gold foil is really cool. If you've ever seen it, anytime you've actually seen like a book, like really fancy books with gold on the edge, gold is very, very stretchy, and you can actually pound it in what we call gold leaf or gold foil. So gold, because of its properties, can become so thin that you can actually get it down to 2,000 atoms thick, which, while that number sounds like a lot, is actually very, very thin when we're talking about atoms. We figured out later it was 2,000 atoms thick, but that was that. All right, so Rutherford shot these particles called alpha particles, which have a positive charge. He shot it at the gold leaf, and I got a picture on the next slide that shows the setup. So what he expected to happen was most of the stuff should go through. These alpha particles, they're radiation. Normally they have to be blocked by lead to kind of keep it in there. So he shot this at there, and what he saw was most of the bullets passed through. They went right through the gold foil, which is, we're calling them bullets, but these alpha particles. They went right through, which is exactly what was expected. But the biggest issue is some did not. Some of these bullets bounced off. So a lot were deflected, so like these ones here, and then some actually shot back as if they'd hit something solid. When Rutherford did this, he referred to it as, it was if I shot cannonballs at a Kleenex and they'd bounced off. That's how much energy he was expecting from this and why it threw him off. So why it was so surprising. So here's a picture. This one is the same picture that we had before. This is more of what is set up. So we had the radiation source. This is where the alpha particle, we use the Greek letter alpha, it's where they came from. You notice the rest of this this was lead, and there was just a tiny little hole in here for the particles to go through. And what he had was this material around the outside that when struck by a alpha particle would light up. So what he saw was most over here, there was a lot of little lights from this alpha particles going through. But he was seeing these ones off to the side and some that went straight back. And we realize now what's going on here in this picture, but we'll talk about where it's the idea like there's this, here's what he came up with. So Rutherford's model, what he realized was, so most of the particles went through. So we realized that the gold atoms were mostly open space. It's the only way those particles could have come through like that. But there had to be something there in the center that all these things were hitting off of. So Rutherford concluded that an atom has to have a small, dense, positively charged center that was repelling his positive bullets. And that's where they would only have repelled if they were positively charged and positive charge, right? Because remember, positives and positives repel each other. So that's why he was getting some of those bullets that were, they were going in and they were going off, they go off at an angle like this. So that would only happen if you had a positive charge there and a positive charge getting bounced off. And he knew his bullets were positive charge. He knew these ones were positive charge. So that's why he was able to determine that the stuff in the middle. He said that he called the center of this atom the nucleus. It was him naming stuff after the cells. It's like the center of a cell is a nucleus, the center of an atom. He also called the nucleus. The biggest thing is he knew, because most of the particles went through, he knew that most of the atom was empty space, but the nucleus there, so the nucleus was very, very tiny compared to the atom as a whole. So the big thing was, this was Rutherford figuring out that all of the atom's positive charged particles had to be in the nucleus right here. So he still thought that the negatively charged particles, the stuff that Thomson was thinking this were the plum pudding model, they knew that the electrons had to be scattered around out here, but so Rutherford still put them out there, just kind of scattered. The idea, again, I think part of where he came up with the nucleus, you think of a cell where you have a nucleus in the center of the atom, or it's nucleus in the center of a cell, and then all the other stuff's around the outside. That's kind of what they're envisioning on this. It was the next set of experiments that started taking it somewhere else. So the next improvement to the atomic model was what we call the Bohr's model. So in 1913, Niels Bohr was a Danish scientist. He proposed a improvement, which we're going to talk about, where he put electrons in a specific place. He's also kind of a badass. He was he ran multiple triathletes, like triathlons. He also, any person who had their face put into a Simpsons episode, even as a corny joke, is my kind of guy. So Bohr's model has the electrons moving in definite orbits, so around the nucleus, like planets go around the sun, which is what you kind of see in that picture there. He called them orbits or energy levels, and they're associated with certain distances from the nucleus. And we'll talk a lot more about this in class, but this is kind of that traditional model of an atom that we've seen, where you have a center nuclei and there's electrons around a circle, and electrons around a circle, and electrons around a circle orbiting around those spots. So that was Bohr. We'll talk more about his evidence where that came from in detail in class. The next model was the wave model, and this is closer to what we currently have. This is the idea that the electrons are kind of moving. This is kind of a cool little animation on it, but we'll talk a little more here. So the wave model is based on this principle of wave mechanics. So according to the wave mechanic model, electrons do not move around in a definite orbit like planets around the sun. There's locations in which they exist. We'll talk about this one's a weird one. So it works like this. Okay, so the next piece of the wave model is, with electrons it's weird, because basically the wave model says it's impossible to determine the exact position of a location, or an electron. The probable location is based on how much energy it has. This is actually based on the concept of the Heisenberg uncertainty principle. The famous German physicist, and besides working with the Nazis, he actually had quite a lot of impact on the wave model. With him, the idea is that it's actually impossible to measure, because of their size, the actual speed of a subatomic particle and its location at the same time, because the act of measuring its location will change its speed, or the act of changing its speed will change its location. So you can't know both at the same time. So what we can do, though, is because of how much energy it has, we can predict the general location that it's going to be in the model. So it still works out where you have a small nucleus surrounded by a large region of electrons, and that there's always enough protons to cancel out the number of electrons when you have a neutral atom. And then the general location is dependent upon how much energy each electron has. So the electron cloud. So sometimes the wave model is also known as the electron cloud model. So the electrons exist in a range of, the electron cloud is a space in which the electrons can exist. And they are whirling around in that space billions of times in a second. They are not moving around in random patterns, however. They are moving in certain patterns based off of their energy. So the location of the electron depends upon how much energy each electron has. So electrons with low energy are often closer to the center of the nucleus. Electrons with higher energy are further out. And as we'll go into later, there's stuff where they can actually move from one until the other. So, depending on their energy, they are locked in certain areas of the cloud. They have to have certain energies to be a certain distance from the proton. So, electrons with the lowest energy are found in the lowest energy level, closest to the nucleus. And electrons with the highest energy levels are found in the outermost layers of the nucleus. All right, so to summarize, here's how we kind of go. So the Greeks figured out the electrons were indivisible, but that was it. They had no idea on any of the other stuff. Dalton was the first scientist to start doing stuff, so he also believed that atoms were indivisible. They couldn't get any smaller. So this was kind of like that marble idea. Thomson was the first one, because he discovered the electron. He realized, like, all right, clearly there's something smaller than a nucleus, or smaller than an atom, but this is all he could figure out. It took Rutherford to figure out the nucleus was there, and that was where we had both. So we had both the electrons and the nucleus. Bohr was the first one to realize that the electrons are orbiting around an atom in a predictable way. And once we get to the wave model, we have the electron cloud, which is where the electrons are moving all over the place randomly, but at the same time, it's still connected to Bohr's model. So the idea that the orbit, what Bohr thought of as an orbit, actually has to do with the energy level of the electrons, and so that did lead to our understanding in the electron cloud. You notice here we didn't talk about neutrons. There was a scientist, James Chadwick, who discovered the neutrons. It was actually much later. Because they have no charge, they're actually a lot harder to know. Just all you need to know is the neutrons were eventually discovered. So here's an image. So we have Dalton, which is the marble model. Okay, Thomson, which was the plum pudding, where he had a positive substance with little electrons like raisins or chocolate chips in a cookie. Rutherford was the first one to figure out there was a nucleus, but then he still kind of just had the electrons going all over the place around the outside. Bohr was the first one to subscribe energy levels to it, so knowing that electrons have energy and electrons with different amounts of energy are located at different places around the nucleus. And then you have the electron cloud model, which still has those energy levels that you see from Bohr, but the idea is the electrons are moving around in those energy levels in somewhere. So you can't know exactly where they are, you can only know approximately where they are. So we, for the point of our class, has kind of simplified stuff down. We are going to focus on the idea that you have protons and neutrons in the nucleus, and then you have electrons in certain patterns and in certain orbitals going around the outside. But you got to remember that it all kind of connects together with the concept. The wave model is important. So that's the big thing. In science, we use a lot of models. Some models help us understand certain things. So in this unit, we spend a lot of time talking about the Bohr model, because the Bohr model helps us visualize where these electrons are. And it does fit with the better model, the wave model, which is a more accurate model, but it's a little bit harder to work with when you're first learning. So just like when we do Pogles and all that kind of stuff, we start with a basic model and we can layer on more complexity as we go. So Bohr is the one we're kind of focusing on. So that's why this is that more traditional sun and the solar system model, where you have the nucleus in the center and the electrons in rings around the outside. Just know this is simplified, just like a model car is a simplified model of an actual car. So this is a simplified model of what an actual atom looks like. Just a quick note, so you have it in your note. Remember, the protons, we consider them having a mass of 1. They have a positive charge. Neutrons also have a mass of 1, and they are neutral, so they have no charge. And then electrons have a negative charge, and their mass is not actually 0, but it's so small that it's for all practical purposes 0. And then also I have some abbreviations when I write. I already used one in here where electrons we write as an E with a minus sign, neutrons we write as an N with a 0, and protons we write as a P with a plus. So we have those kind of shorthand stuff. You'll see those on different worksheets, different assignments, different stuff. So that sums up our notes on the atomic history.